My name is Fergus Hanson, and I'm on day 14 in my new role as the head of ASPI's International Cyber Policy Centre. It's a job that has a broad remit, as I'm discovering. To my father, I'm the new head of IT, and he's been pretty liberal with handing out my mobile phone to his retiree friends, and I've, in between sessions, fielding calls on updates to Microsoft Word and Adobe Flash troubleshooting. Far more substantively, it's my pleasure to introduce and moderate this session on the impact of new and emerging technologies, technology options. It's an issue that several speakers have flagged as absolutely critical, and we're very fortunate to have a stellar panel that brings both depth and breadth to this discussion. As the previous speaker and others yesterday said, given the timelines for developing and delivering new capability, how does the ADF stay relevant when new generations of technologies are cycling through every 14 months or so? And of course, the issue is not just about adapting and harnessing new versions of existing technologies. It's how we respond to an entirely new range of technologies that are coming down the pipeline. To inform, engage, and verbally caffeinate us this morning, we have Alex Lynch, who is Manager of Public Policy and Government Relations at Google. We have Josh Collens, who is the Director and Senior Technical Advisor to HQ Air Combat Command National Security Engineering Centre at the MITRE Corporation. And we have Jeff Connolly, who we heard from yesterday, who is the Chairman and CEO of Siemens in the Australia Pacific. I'd now like to invite Alex to kick things off with an initial burst on strategic digital enablers and the emergence of machine intelligence. Please welcome him.
All right, hello everyone. I just want to say it's an honour to be here today. There's an underappreciated intellectual art to defence strategy, and I wanted to thank ASPI for fostering that here in Australia and all the people in the room for being here today as well. You guys might ask, why is Google here today? We have nothing to do with defence, and that is true. We are still going to continue on with our mission of making the world's information universally accessible and useful, but there are trends developing in technology that I think it's critically important, particularly for the people who are defending our nation, to be aware of. And because that context is changing very rapidly, and because it can be very important in times of conflict. Now, you guys, well, many of you will recognise this machine, which is the bomb developed at Bletchley Park during World War II, which played a critically important role in the success of our efforts during that conflict. Here we have Garry Kasparov, and you can see this was the photo in 1997 when he was defeated for the first time in chess by a system developed in the US by IBM called Deep Blue. Now, the US support for their defence science and technology led to some critically important breakthroughs that then had both military and economic benefits. The silicon chip and the internet, for example. More recently, about a year ago, we went to South Korea and played using this program we developed in the UK actually, called AlphaGo, to play a Korean Go Grandmaster, and the system performed quite well. We actually had to lay fibre between Google's offices in Korea and the event venue so that this system could access all the resources that it needed, because it was a huge resource hog. And it played competitively and won 4-1, and that was seen as unprecedented at the time because people thought that Go was about 10 years away from being solved. Only a couple of weeks ago, we went to China with a revised version of this technology. And this time we defeated the world number one there 3-0, and he described the experience as very unpleasant and being like playing with a Go god, as he said. Now, a year later, this was running on an entirely new chip, and instead of needing Google's entire resources to run, it runs off a chip about this big, which I'll talk about later. Now, what are we talking about when I talk about machine learning? This is only possible because chess was possible back in 1997 because although Go and chess are both perfect information games, chess has a small enough number of variables that you can brute force it. You can have a computer assess all the possible pathways across the course of the game and decide on the optimal one from its current board position. Go, that's impossible. from the beginning of the game, there are more possible board positions in Go, legal board positions, than there are atoms in the universe. So you can't brute force it. We needed a system that could use, in the same way that Go grandmasters do, something that's akin to almost intuition, to look at the board and decide what it thinks the best course of action is going to be. Artificial intelligence is the broad science of making things smart. Machine intelligence is a subdiscipline which is specifically non-biological, about building smart machines. And then we go to machine learning, which is about machines that self-teach to be smarter. And within that, there are other subdisciplines, evolutionary algorithms, Bayesian algorithms, and the one we're particularly interested in, which is deep neural networks, and we have had success with that at Google recently. How important is this to us? It's the core of all of our fundamental research efforts at the moment. You can see the number of directories containing neural network model description files at Google here, and how fast that has accelerated over time. We've recently trained 12,500 of our engineers to work specifically on this technology. And what does it look like in practice? It makes things like this possible. So this is part of Google Translate, in that you can hold your camera up to signs and wherever you are in the world, and it will translate those in real time through optical character recognition and translation technology. We translate about 1 billion search strings between different languages each day, and this is all run by a neural network. And now this neural network is now able to actually translate languages it hasn't even been taught to translate before. For example, if it knows English to Portuguese and English to Spanish, then it can then figure out for itself how to translate between Spanish and Portuguese. Now, if you have photos in Google Photos, you'll be able to search for a dog, for example, and it will bring back all the photos of a dog without you having to label that there is a family dog in the photos. It will just assess what's in those images. It's also very difficult, and you guys would have probably seen this if you've ever tried to use voice recognition on your phones. It's been quite terrible until recently. Now we're actually getting to the stage where this technology can recognize people's voices, can translate between, I think, about 55 different languages at the moment in voice. And we're seeing about 20% of searches come through on voice as this technology improves. And computing will probably change over time to be more ubiquitous, less sitting at a computer and tapping away, and more having computing in your environment you can access. It also has practical back-end applications beyond our consumer products. So for example, we used machine learning on the variables that we control in our data centers to reduce the energy consumption by 40%. And as you can imagine, at Google, data centers are our main cost. That's where we run all our operations, run our cloud technology and machine learning, where we store data. And a 40% reduction in energy costs in the data centers is actually hugely significant for us. And that was achieved by training this neural network in a separate trading environment and then deploying it to the data centers. And just, you can see the results there in the graph. When we turned it on, power consumption went down, flicked it off, power consumption went back up. So this stuff isn't magic, but I wanted to give you guys all a bit of a fundamental explanation of what this technology looks like, because it's emerging across not just at Google, but across the entire economy, and I think it's very important for us to all here to understand what the future technological environment is going to look like. Previously, computer coding, which goes into almost all of the technology we use each day, that isn't explicitly mechanical in basis, it used to be that you had to explicitly tell the computer what to do. So, for example, spam, but this could equally be a cybersecurity problem, you'd have to tell it specifically what to look for and what to exempt. Now, you tell it the outcome you want. So I want less spam, and give it feedback on that, to tell it which items are spam and what you're getting, and then it learns over time to edit out those spam emails, which is why you barely see, if you've got a Gmail account, I don't know if any of you here do, I hope so, you'll almost see no spam emails because 99.9% of it is all just cleaned up by an algorithm. It's hard to conceptualize how difficult it is for a computer to actually do some of the stuff we take for granted, like vision. So we might see a line here, the very, very simple object. The computer sees shades, ones and zeros, needs to basically apply a mathematical model to them so that it can understand them. And you can understand how this gets hugely complicated once you move beyond a simple blob to what we see out here in the real world. This is how it works in practice. This is how you train a neural network, essentially, at a very high level. Feed it an image, and we want it to come back and say, this is an image of a cat. The model says, you know, it might say this is a tiger, this is an animal, this is a dog, whatever it happens to be. And then you have those images labeled, which you then feed back into the network, and you tell it this is actually a cat, and it changes its internal parameters and tries to spit out more accurate results in the future. And you do this again and again and again, and iterate and iterate and iterate until it gets more accurate. And then you can start feeding it images that it has not seen before, that aren't labeled, and see whether it can label them successfully. And again, you train and train and train, and it gets better and better. And this is what it looks like on the inside at a conceptual level. So that layer at the bottom might be the dots and assigning the values to the specific images. Next layer might be identifying lines. Next layer might be connecting the lines into shapes. Next layer might be abstracting the shapes into 3D images. And the next, it might guess what the overall construct is. So it basically proceeds up the layers of abstraction. And this is something our brains do automatically, but it's very, very difficult to do as a computer program. So why is this happening now? Why is this all taking off? And you guys will probably recognize this image as the Wright brothers' 1903 Flyer. The internal combustion engine already existed when they were building this plane, but it wasn't optimized for flight, and they needed to design an entirely new engine to make this thing take off, which is what we've had to do with computing as well. So the PU on each of these things stands for processing unit. It's basically where the computer does the operations that make it run. So the CPU is what we've had around for a long time, the original computing technology. You can think of it as almost a family sedan, a Honda Civic or something. So it's really, really good at getting you from A to B. It's not that fast, but it's a really good general purpose machine, and it's great value. It's very cheap. GPU can handle more complex mathematical problems. It's great for graphics. It's great for some of these scientific problems. But it's got a lot of bells and whistles. It's very precise and not entirely optimized for machine learning or what we want it to do. It's more like a Porsche, if you will. So we tried to come up with our own technology that would do this one thing specifically very, very good. And so we created, about a year ago, we released this thing called the TPU. Now you can think of this as more of a drag racer. It's unbelievably fast in a straight line, 15 to 30 times faster than these other chips, but it can't turn at all and it can't carry any groceries. It's very good at just this one delivery implementation. A year later, we've come up with an entirely new chip that solved a few of those problems. This is the second generation TPU. This is more like a Formula One car in that it's very, very good at going around a track very fast. And much like the OODA loop, Formula One itself, machine learning, learning those algorithms is all about iterating and making cycles and feeding back into the machine and make sure that it learns over time. And this intensive process is being made a lot easier. Now each one of these things, and this is what I was talking about earlier, which we ran the new AlphaGo program on, is about 15,000 times, performs about 15,000 times more operations per second than that Deep Blue machine that defeated Garry Kasparov did. And you can see racks of these in the background. We're pleased with this technology, but it's important that it's not only us that gets the benefits of this. So we've made about 1,000 of these available to machine learning researchers, for example, and we are sort of democratizing this technology. That's Google speak for just making it as widely available as possible by making it available to companies who want to use it on the cloud. So it's not just, I've explained why computing power, we're only really getting to the stage where we have the right computing power to make this technology work effectively, but it also needs other things that we've built on. It needs connectivity. The mobile and data networks we've built up over time. It needs data feeding back into it, so from people's mobile phones. An example you might think about is the Google Maps. We needed the cellular networks. We needed people to have mobile phones. We needed the apps to be feeding data back into the network. We needed a neural network to be able to optimize the travel patterns over time. And with all of that tied together, we've finally gotten to the stage where we can optimize travel patterns for everyone who's using this technology across a whole city and make people collectively's days a bit easier. So this stuff isn't magic. It's basically just a new engineering tool set, I think, that everyone who's interested in developing technology for whatever systems they are needs to be aware of. So what's happening with it outside Google? It's one thing for us to be doing it. We base our company on this technology, but what's happening outside? So we've made a lot of this stuff publicly available through open source and using this TensorFlow technology. Now, one of the examples actually comes from Australia. This is a dugong, sea cow, manatee, whatever you want to call it. the problem with studying these creatures is they're very hard to find. They live out in the ocean, so biologists need to better understand their travel patterns, their population densities and the like. And this is what they have to work with. About 40,000 of these images collected by low-flying aircraft and drones. The researchers have to go through each one of these images and find the dugongs. So it's basically an image problem. There it is. So they basically used a machine learning deep neural network to go through these images and learn to identify when there were dugongs in the images, and could basically save the biologist who was doing this the entire workload that they would have had going through 40,000 of these images in very fine detail and trying to find these creatures. Instead, they can work on the science and the scientific response to any problems they find. It's also being applied across a wide variety of medical technology problems. Diabetic retinopathy has actually become very easy to diagnose, and the systems can diagnose breast cancer actually with a lot more accuracy than a trained pathologist. Again, an imagery intelligence problem. Airbus Defence and Space is using cloud machine learning to identify when the images that satellites collect have clouds in them. Obviously can't use those images or provide them to customers, and so they just automatically screen those out using this technology now, instead of having to pore over the images. So hopefully I've given you an example of how this technology has been used in practice right now and fundamentally how it works, but how is that applicable to your work? Just consider the unsolved problems that you have. So obviously imagery intelligence and preserving those valuable skill sets is going to be important. People retire and move on. This is similar to the medical community. When you have a highly trained doctor who's good at assessing these images, you want to preserve that knowledge. But also things like logistics and supply chain optimization. You could feed variables in cloud patterns, the weather, the routes, the camouflage you use, the emissions that vehicles are emitting, whatever it happens to be, and try to optimize, what is optimized for survivability, optimized for delivery times. You could use it to lay out bases in hostile territory so as to minimize line of sight to vulnerable areas, for example, from the surrounding terrain. Now, those are just some things off the top of my head, but Google itself isn't a source of all creativity, and the most important thing for me is for people each of you to be thinking about how this sort of technology could be put to use to save people's lives. Now, I wanted to provide a few resources if you guys do have any people on your teams who might be interested in looking at this stuff. You can just go on, and it's all free and open source, and I can send this slide through ASPI to anyone who's interested. And there is also commercial resources available via cloud. But the most important thing is to think about, when you think about how you could use this stuff, is to think about the data sets you're collecting. Obviously, you need a lot of data to train these models on, and sometimes before you even start applying this technology, you need to be thinking about the data that you're collecting and both negative and positive examples so you can provide that. Now, I've actually got a quote that I should get out right now, because although I have tried to explain it as clearly as I can, there's nothing better than hearing from someone from your own community. So, to give you an example of who's thinking about this, Lieutenant General Louis Gauzy, director of the Chinese Central Military Commission Science and Technology Commission, said that the world is on the eve of a new scientific and technological revolution, and that we're transitioning from an era of informationized warfare and entering the era of intelligentization. So thank you for your time.
Thank you very much, Alex. I'd now like to welcome Josh Collens to the stage. He's talking about designing today's force to accommodate tomorrow's technologies.
Good morning. I'm Josh Collins from the MITRE Corporation, and this morning I'm going to give a brief overview on a technical approach to evolve and deliver Multidomain C2. Before I dive into that, I want to put a little context and background on Multidomain C2. It's clear the military leadership is recognizing the need to integrate across domains to be more effective against our current and emerging near-peer threats, I think we heard that loud and clear yesterday from the Vice Chief in looking at that one domain, warfighter domain. The leadership also recognizes they need to enhance their situational awareness to understand what are the optimum resources that can be applied to the kill chain to achieve that effect that they're looking for. And they believe multi-domain coalition C2 friendly forces is really going to be the foundation of how we're going to fight wars in the future. So what are the challenges if we're to achieve multi-domain operations? Based on our analysis at MITRE, let me just say command and control within a domain is challenging enough, but when you're looking across multiple domains, it really becomes quite a complex problem. We've come up with probably 3 major challenges that the military is going to need to face as they embark upon this journey. One is integration. And it's really the integration of cyber and space into your more traditional domains, whether it be maritime, land, or air. I know yesterday there was some discussion that the ADF does not recognize space as a domain. I will contend that it is a domain, and in the United States we've actually gotten to the point where it's now considered a warfighting domain. Space can be characterized as the 3 C's: competitive, congested, and contested. Competitive, obviously, is the proliferation of commercial, and I honestly believe commercial is going to set the policy for space as we continue to explore CubeSats. Google's going to have a big role going forward in space. Congested. Space is a global tool. It's just not the United States anymore or Russia. It's China now has an active role, and a lot of other countries are getting actively involved in space. And then there's the contested part. Based on some actions from our near-peer threats in the past couple of years, the United States has decided to take on or stand up a battle management capability for space if, in fact, the conflict should evolve into space. Obviously, space is a critical asset to our combatant commanders, and it's very important that we protect those assets so we don't really lose our eyes and ears as we go into conflict. The second major challenge is speed and agility. The ability to integrate across domains and meet the operational and tactical timelines is going to be a challenge. When you look at the OODA loops, so to speak, within each domain, they vary greatly. So the ability to synchronize across those OODA loops to achieve that common effect will be quite a challenge. It's going to require a lot of experimentation and exercise. And then the third major challenge that we see is really scale. Multi-domain needs to operate at a global level, and I'm pretty sure we heard that extensively across the ADF service chiefs yesterday. The concept of operating in a single AOR is going to continue, but if you look at our near-peer threats, they're really operating at a global level. And multi-domain needs to support that global level and be able to apportion its resources across multiple AORs as we engage our near-peer threats at the global level. So, what are the essential capabilities that are required for multi-domain operations? Well, clearly, multi-domain needs to support deliberate and dynamic planning and support the execution with the optimal set of assets. I already spoke about the situational awareness, but it's more than just being aware of what's available to package certain forces to achieve an effect. You've also got to carry in your ISR assets, and they need to be bundled closely with the force package or the objective or the mission that you're trying to achieve. The third essential capability, and I believe this is brand new, maybe not brand new, but it's going to require a lot more experimentation and understanding, and that is, what is the probability of kill for a non-kinetic effect? Kinetic world, we got it. We understand what that missile, what that bomb is going to do, where to drop it, how to drop it. based on wind, whatever, you know, if you got the thing called a JMEM, it doesn't exist for non-kinetic effects. So what confidence are we going to give to the commander to pull that trigger to, say, perform a cyber offensive attack? And what's the probability of success or kill? That's going to be essential, because I think as you start to look at the integration of non-kinetic and kinetic effects or across the domains, that's going to be the wave of the future. It's just not going to be one here. It's going to be a synchronized package across both kinetic and non-kinetic. And the understanding of the probability assessed for non-kinetic is going to be crucial for the commander to have confidence in order to pull that trigger. So, changing gears a bit, given the context of multi-domain at a very high level, what is the technical approach to achieve that? And we call it owning the technical baseline. I think we heard that pretty clear from yesterday through the leadership. When we're talking about owning the baseline, we really think the government needs to do that if they want to evolve and deliver MDC2 capabilities. And what does it mean to own the technical baseline? Well, the government fosters a collaborative relationship with industry participation. Industry doesn't own the technical baseline. The government owns it. When the government owns the baseline, it offers industry to demonstrate their wares, but in a more controlled environment, meaning they're complying with their specifications and interfaces. And I'll talk about that in a minute. It allows the government to pick and choose which vendor they want to go with from the capabilities among various vendors. And this prevents what we call vendor lock, sole source solutions, or proprietary solutions. And we think this is a vital approach going forward to achieve, to achieve any major acquisition, but specifically in this context for multi-domain. To achieve owning the technical baseline, there's a supporting framework that consists of 4 major components. And if you look at the slide, I'm assuming on the upper left, there's this thing called the Government Reference Architecture. And that is an open layered architecture. I believe the CEO from Lockheed Australia talked about this yesterday as well, which is great. And, but the government owns that, and they own the interfaces and the specifications, and they publish those for industry to build towards. Very similar or akin to the app store that you see on your iPhone. But the government, or in this case, the architecture is managed and owned by the government. Industry will build their products to adhere to those standards and leverage those common services. So now you have complete modularity, and it's a layered approach where you're not locked into a specific vendor or third party. The next component, if you keep moving down to the lower corner, is we really want to take the functionality and break it down into modular components. In the past, we've built pretty big monolithic systems, and as we know, over time, they get very brittle, they're very difficult to maintain, and they're very difficult to change. What you really want to do is break it up into components and then manage those components operating on that common infrastructure through your government reference architecture. Going up to the upper right, this is probably one of the key cornerstones of the approach, is the government provides a government-owned system integration laboratory. And this is where you bring in all your key stakeholders to collaboratively build and integrate capabilities. Stakeholders could include from your acquirers, to your users, to your testers, to your industry partners. We think this is a best practice going forward. If you think about acquisition in the past, and I think yesterday someone said between 5 and 7, I will contest it's more like probably 10 to 15 years of development. The goal here is to do continuous development with heavy user participation. In the past, the user would define their requirements, they would let a contract, maybe 10 years later, the system would show up. We have no idea if it's still going to meet the current threat. Does it even evolve with the technology over time? The users have changed out probably 3 times before the final system's delivered. So the goal here is to do continuous development, heavy user involvement, and I think someone said the concept, which I totally support, is build a little, test a little, feel a lot. And I think this totally supports that construct. And then finally, in support of that, we want to have a continuous pipeline of capabilities. In the commercial world, they call that DevOps. And this is really based on Google as well as Amazon. If you think about Amazon, they put out a new software probably within minutes, daily. And the goal here is to automate the development process to take care of those behind-the-scenes things like testing, security requirements, interface compliance, and so forth like that, and really focus on what are the capabilities that you're trying to deliver for the warfighter. So when you take those four major components together, you basically have created an environment where you're owning the baseline, and it results in a repository that can be shared with industry. It can demonstrate, will show what the specifications, interfaces are. It'll allow the industry to see where your baseline is, what are your needs, what experimentation do you want to run to further develop and define your requirements or mature your ConOps. So it's an opportunity for the government to be actively involved, take ownership, but partner with industry together moving forward, but in an open way and in a controlled way. I'm not proposing that the government actually be the one managing the baseline, but clearly they need to be the ones owning it versus handing it over to a vendor, and when you get into that single vendor lock. And might be good for the vendor, but it's not in the best interest of the government. So continuing down that path, this is a notional reference architecture for multi-domain. We look at it as a system of systems approach, bound by two entities or two different domains, whether it be the theater or from a global perspective. But it's really a federation of capabilities that can be used across domains to achieve that common effect. It allows optimization of resources to achieve that effect or that objective. I think the other key part here is they communicate across a common bus and a message set that all the entities understand, so each entity or each capability is highlighting what their situational awareness is. It gives the commander an opportunity to repackage, redynamic. This is kind of the machine-to-machine that we heard about yesterday as well. And it allows the balance of resources across the theater, so to speak. So you're optimizing resources for this specific versus that specific. If I was to take an example through the architecture, if you look at the theater C2, for example, the purple boxes really represent what are the missions you're trying to accomplish within the theater. And then if I take, joint fires, which is clearly a common topic, was this morning, clearly was yesterday. What is that force package I want to achieve or put together to support joint fires? I mean, we could start with a cyber attack, take out a power plant, for example, and then we could follow it up with a Navy, Tomahawk, and then we could have the Army's ground fires, and then once the belly's soft, then we can come in with a final strike. This is the integration that we're talking about across the domains in achieving that common effect. And what is the architecture that allows that to enhance both the command and control and the situational awareness that's required to optimize your resources? Coupled with that, you really need to think about your data strategy, and I heard that again yesterday and again today, I believe. I think what I heard yesterday, and I totally support, is that as you start to integrate across domains, there's going to be a vast amount of information. Some of it might be useful, some of it may not. MITRE likes to use this concept called the loose coupler approach, where you really focus on what is the minimum set of data I need to achieve an objective or an effect. For example, what I have here is what are the options or what are the course of actions to defeat or counter an IADS? And there might be three course of actions, whether it be an Army kinetic against a radar, Air Force cyber against a power station, or Navy EW against a communication. Now, this is notional, but I think the example illustrates what I'm talking about. And then what is that minimum set of data that I need or the commander needs to make that decision on what the right course of action is to pursue that? We think this is very valuable in getting to the minimum set of information you need between your different capabilities in order to achieve that effect that you're looking for. versus this volume amount of information. Don't get me wrong, we still need data analytics, and we still need to provide that, but as you get down into the kill chain and the execution across your joint fires, you really want to get down, what is that minimum set of data that you need to perform your mission. To exercise the architecture and the data strategy, we think it makes good sense to go use a set of operational threads that are relevant and provide operated use cases, working jointly with the operators. And this is an opportunity to really exercise your architecture as well as understand your data strategy and what your data needs are. So for this particular example that we have here, what is the optimal tasking for airspace cyber to locate a high-value target? What is the apportionment of an F-35 in support of an intelligence, surveillance, and reconnaissance? We all know the F-35 is a very special fifth-gen aircraft. It's just not a strike aircraft. It has many capabilities that we probably don't even know how we're going to operate in the future. But this allows you to experiment and test on how, what to best use and optimize your assets. And then, what is space bringing to the table? What are available and what capabilities do they have that could also assist in determining where that high-value target is? So the goal here is really to exercise through the use of use cases and determine how to best implement a multi-domain operation in the most efficient and optimal manner. So MITRE is very much committed to, from a company standpoint, from our CEO down, to really get multi-domain off the ground. A lot of people say we do it today. I agree, but we don't do it at scale. And it's not factored into any of the real joint force planning that goes on from a campaign perspective. So MITRE is, through its own internal funding, is kicked off an initiative where we're going to build out this government reference architecture, looking at standing up a SIL, clearly working with our industry partners. In fact, I have a industry day in Washington, D.C. back in July to kick this off. And then obviously work directly with the user community and determine what those appropriate use cases are to exercise the architecture, and then have a facility where we can continually bring in the operators and get their feedback. I will offer, I welcome ADF participation if they so desire, and if they do, we can work out the mechanics on what level of involvement they like to be. I think I said in the first opening remarks that, at least from the leadership, they clearly see multi-domain coalition C2 friendly forces as the staple or the foundation of going forward. So as we go forward, I highly encourage the coalition partners to participate, whether it be here or overseas or in the United States, but we clearly need to address the partnership both from our allied and our coalition partners. So in summary, I think the leadership recognized to be effective against our near-peer threats, we need to work across and integrate across multi-domain. Clearly, I believe that's where the ADF is headed. It needs to be agile. It's really an optimization problem as well. What is the best maximum use and integration of resources to achieve that effect or objective? To get there, I really believe the government needs to own that baseline. Air Marshal Davies said it yesterday, and I had a brief conversation with him afterwards, and wholeheartedly supports and endorses this concept that I'm espousing you today. And it needs to be a partnership between the government and the industry. I heard a lot of that yesterday, but I think the government needs to control the architecture to allow multiple industry partners to play, but manage those interfaces where you can still protect the vendor's IP, but it's in a controlled fashion, and you're not sharing across other, and you're not, clearly not looking at vendor lock. And then finally, obviously, there is a lot of cultural barriers in achieving multi-domain. We heard a lot of, everybody's in their domain, whether it be air, maritime, and obviously with the bringing on of cyber and space, which is going to have a huge role, I believe, in the future. We're going to need excessive experimentation and exercise. And it shouldn't be just an exercise where, okay, great, everybody gets together and goes home. It really needs to be tied and vetted through an experimentation campaign plan where you're trying to satisfy a specific set of objectives that you can continue to evolve and move forward, both from an operational and a technical point of view. With that, that wraps up my presentation. Thank you.
Thank you very much, Josh. I'd now like to invite Jeff Conley to come along. He's speaking on intelligent transformation of data, automation and digitization.
Thanks again for inviting us to join Peter. The impact of new and emerging technology options. I think from all of the discussions we've had yesterday and today, there's no surprise when I make the observation that the whole environment is dominated by the conversion or the acquisition of and the conversion of data to some sort of decision making and changing something. The collection of data for its own sake doesn't achieve anything. And in many forums I talk about the comparison between the Internet of everything, things and services, and the industrial internet to make a comparison. At the end of the day, there will still be things and there will still be people, and the internet is a means to actually expand our decision-making capability. From an industrial perspective, and if I talk about then data dominating the environment of decision-making and doing things differently, clearly born out of the competitive environment of industry, there's a need to have shorter cycle times, less non-conformance costs in a build, in a project. There is a massive increase in the front-end engineering going on in projects. If I consider where the Industry 4.0 discussion started in the factory walls, the idea that you can actually envisage a cyber-physical world where you're doing a lot of front-end engineering, not just of the product itself, but of the manufacturing process. And if you're capturing enough data up front and doing your engineering in enough detail, then the transition from the design through to the production line and actually the life cycle of that production line of product are truly interactive. And in that process, if I can ask you to picture that in a world where we have PLCs, programmable controllers, for example, and you have a controller, you take it to an application, you start configuring, doing the systems integration. If you do enough front-end digital work, there will be no systems integration because it's done in the front-end engineering, and you transfer that data straight in to the automation processes. So there'll be quite some disruption happening in the systems integration world. As I said, reducing non-conformance costs, that was where the whole thing, I think, from a manufacturing environment started. And of course, we talk about whole-of-life costing and upgradability and maintenance. Siemens, as I mentioned last night, spends 6.5 billion Australian dollars per year on its R&D core technology focuses, and I'll just read through them and I'll pick on a couple because a number of them have been covered by the colleagues on the stage today. Our focus areas are in the area, not surprising, of simulation and digital twins, data analytics, deep learning, artificial intelligence, autonomous machines and vehicles, additive manufacturing, power electronics, energy storage, integration and management, IT security, the industrial Internet of Things, the connectivity technologies, sensors, networks, and connected e-mobility. So if I, again, just pick on a couple of themes to give you an idea of what's happening and the sorts of breakthroughs that are now occurring in the processes. If I talk first on additive manufacturing, lots of people talking about it. You hear it discussed in medical environments about hip replacements, joint replacements, rather static sorts of applications. But if you think about the opportunities and how logistics of spares will change with the advent of additive manufacturing, Siemens has just produced 13 megawatt gas turbine blades. Now, these nickel-based super alloys in construction, they move at 1,600 kilometres an hour, they take 11 tonnes of load, and they operate at temperatures of 1250 degrees C. And these are really in life now. Picture a turbine sitting on a vessel which breaks a blade. Spares might not be there. Historically, those blades would be manufactured somewhere off in the world where that plant was originally manufactured, and it would take some shipping time, and it would finally make its way to the field. Additive manufacturing, of course, changes that logistic. The value of a spare is in the engineering design and the composite that actually that blade is going to be made out of. You send the software packet to a location which stores different composites, and you print your spares on site as close to the application as you need. So quite some dramatic changes. Therefore, composites and material sciences are really taking off in those fields. Powders, how to mix, as I mentioned before, superalloys. Those superalloys, of course, dramatically change the characteristics of weight, strength, temperature, operating ranges, parts, assemblies, sub-assemblies. The cyber-physical virtual engineering world is already expanding the physical limits that we operate in. I mentioned, and I'll keep mentioning, I have a side job as the chairman of the Prime Minister's Industry 4.0 task force, and why I think that's a valuable thing, not just for the industrial application, but in many other adjacent fields and applications of products that move out of industry into, for example, defence. Industry 4.0 is a framework that concentrates on the view of the future of the cyber-physical world. What are the technologies that are going to need to be developed to actually live in that world? What are the standards? What are the reference architecture standards and norms that we're going to have to use to make that as seamless as possible? And there comes for me a little paradox when we're sitting in the defence domain saying, well, we move very much more to open systems, open architecture that is transportable, and to what extent can defence actually or need to access those open domains on a global level, not just within our own domain. I was fascinated yesterday at the discussion about, of course, correctly, that we want to be an integrated Australian Defence Force, but there is a level above that in terms of the collaboration that we need to be doing to access data and breakthroughs in other domains. So the interoperability, the cross-domain sharing, at the end still relies on technical standards being developed, and that they are not developed by individual organisations for their own single purpose. That is in nobody's best interest. I mentioned last night that Siemens had over a period of time acquired and developed a series of software tools, virtual engineering collaboration tools. That spend over a period of 10 years is about 13 billion Australian dollars to assemble those dynamic modelling environments that we know are going to be much more important in the field of manufacturing. Advanced manufacturing is a terminology that's crept in, and at the end of the day, the value in manufacturing the future will be much more towards the engineering design part at the front end. And if we take the total value of a product over time, the value is generated by the engineering design intelligence that's built into the front end, and not so much the parts itself at the end of the process, and not so much the screwing it together at the end of the process. BAE, for example, is doing already dynamic stress modelling on entire assemblies and sub-assemblies. An interesting story that I like to tell is an application for NASA, the Mars rover jet propulsion system. The challenge is that it's taking a 2,000-pound landing vehicle. It's operating at 248 million kilometres away. It's got to withstand temperature ranges of 1100 C to minus 200. It's travelling at 20,000 kilometres an hour, and it has to stop in 7 minutes. If it doesn't, then you can imagine the consequences when it hits the surface. You get one chance. And these are not things where, in the digital world, we do prototypes anymore. They're done in the virtual world, and they have to be done with so much exactness that it works, and it works the first time. When you push that button to fire that weapon, it will work. We talk a lot about the transition to predictive maintenance. In a corporate way, we talk about risk management, but typically most organisations do risk reporting. They don't do terribly much risk management when it comes to actually changing something. If I take an example of trains, banal example of trains, what is it that makes a train run on time? And you would think that's the electrical propulsion system will make the train stop. It's actually not the case. Bearings are the problem, and believe it or not, train doors are the problem. What makes a train run late? You can't get the passengers on and off the train. And if the doors break down, that won't work. They stay on the train, or they don't get in the train. The question is, can you actually simulate and through computational mathematical models with enough data, predict when that's going to fail? We, at the moment, on the very, very fast trains in Europe that run at 350 kilometres an hour, real time, measure individual bearing temperatures. And we can tell with high confidence levels that a particular bearing on a particular wheel is going to fail within 2 to 3 weeks. So that particular bogie has to come off the line, otherwise they get a delay. So working out what's the most important thing for the mission, being on time, and working backwards. There's no point having an LHD if the propulsion system doesn't work, because it sits in Sydney, and it's a topic very close to my heart right at the moment as we work through that interactive analysis of what's happened there. I mentioned last night, energy and the technologies in the energy domain are changing dramatically. Siemens and Airbus, for example, are spending triple-digit millions at the moment already talking about electric propulsion. Electric propulsion is taking an increasing role in surface and, of course, subsurface applications through defence. Topic then, of course, comes what are the energy storage technologies that are relevant if you're moving in that direction. We've had a dialogue in Australia. Most of you will have heard the dialogue on energy storage. And we had a great marketing guy who offered Australia 100 megawatts of power in 100 days, or it's free, including some fries, I think, and some apple pie at the end there. The truth of the matter is, depending on the application, there are many different storage technologies. Supercapacitors at one end, if you're talking about low megawatts for seconds, or you're talking about months of storage. And the months of storage discussion, you end up at pumped hydro, you end up at hydrogen. And hydrogen is the most dense carrier of energy of any of the gases. It will come. And the ability for Australia, for example, to generate hydrogen through renewable sources and apply it in fuel cells, in energy storage, is certainly something that will change our thinking on energy generation. So at the end of the day, there will be different forms of energy. We're working together with the DST group on high-temperature superconductor motors, which will be a natural successor. We originally, Siemens, were supporting the German submarine proposition. We already talked about what would be the successor of Collens class in the electrical motor field. Permanent magnet motors, fine. If you move forward, you must be reducing weight. You need to be able to reduce the weight by 30%, the footprint by 30%, and you actually must increase the distance via different forms of air-independent propulsion. But high-temperature superconductors is certainly a thing that will move into the whole motor and generator environment, and in fact, if we talk about ships, into that microgrid that exists on a ship. As I offered last night, in industry, energy, mobility, infrastructure are increasingly interdependent. And as the colleagues have spoken about, cross-domain capability depends very much on the standards you put in place up front, so that you don't waste resources as you move down the track and actually realise that those two systems you've put in place don't talk to each other. And the sub-optimisation, if we don't do that in the front end, is rather large. In summary, the primary force, from my point of view, is, of course, the data digitalisation, computational analytics, as the colleagues have mentioned, as we move to artificial intelligence, deep learning, mathematicians. The group of people that are running those train analyses on doors, they're mathematicians. The ability, the data sciences behind the maths, behind the simulation requires a different set of skills. As I mentioned before, the trend is very much to open systems. And the challenge, of course, for defence in the environment where there's many more open systems and there's much broader network with many more devices. How are we going to protect major assets, distributed assets that are subjected to many more points of control? Thank you.